Tonight, we're going to talk about the most ambitious journey humanity could ever attempt. A journey to Andromeda, our nearest major galactic neighbor. That faint smudge of light you can see in the night sky. We're going to explore what it would actually take to get there, to cross the intergalactic void and reach another galaxy. And by the end of tonight, you're going to understand why this mission would push every human limit to the absolute breaking point, and why even attempting it might be the most terrifying thing we could ever do. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Andromeda sits in our night sky like a faint smudge of light. You can see it with your naked eye on a clear, dark night, hovering in the constellation Andromeda, looking like nothing more than a fuzzy patch against the stellar backdrop. Ancient astronomers catalogued it over 1,000 years ago. Persian astronomer Abd al-Rahman al-Sufi described it in the year 964 as a small cloud. For centuries, nobody knew what it was. A nebula, perhaps, a cloud of gas within our own stellar system. It wasn't until the 1920s that Edwin Hubble proved it was something far more profound, an entirely separate galaxy, a vast collection of hundreds of billions of stars sitting outside the Milky Way. The Andromeda galaxy contains roughly 1 trillion stars. That's 1,000 billion individual suns, each one a nuclear furnace fusing hydrogen into helium, pumping out light and heat across the cosmos. Many of those stars likely host their own planetary systems, worlds orbiting distant suns, perhaps some with conditions suitable for life. And here's what makes Andromeda both fascinating and terrifying as a destination. It's 2.537 million light-years away. That distance is almost impossible to comprehend. Light leaves Andromeda, travels at 186,000 miles per second through the vacuum of space, and reaches Earth 2.5 million years later. When you look at Andromeda tonight, you're seeing light that left that galaxy when early humans were just beginning to emerge in Africa. And the light you're seeing now started its journey back then. That light has been traveling through space for longer than our species has existed. So, when we talk about a journey to Andromeda, we're not talking about a trip to Mars that takes 7 months, or even a trip to Pluto that takes 9 years. We're talking about crossing a gulf of space so vast that it fundamentally changes what it means to travel. Let's start with the most basic question. How long would it take? The answer depends entirely on how fast you can go. And that's where the nightmare begins. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour when it's diving close to the Sun. That sounds incredibly fast. It is incredibly fast by any human standard. At that speed, you could circle the Earth in about 3.5 minutes. You could fly from New York to London in about 45 seconds. But let's do the math for Andromeda. 2.537 million light-years. That's about 14.9 quintillion miles. At 430,000 miles per hour, the trip would take about 3.9 billion years. That's almost the same as the current age of Earth, which is 4.54 billion years old. By the time you arrived at Andromeda, if you had left Earth when it first formed, you'd be arriving just about now. The entire evolution of life on Earth, from single-celled organisms to dinosaurs to mammals to humans, would have played out during your journey. Obviously, that's not acceptable. So, let's talk about going faster, much faster. Let's imagine we could build a spacecraft capable of traveling at 1% the speed of light. That's 1.86 million miles per hour. At this speed, you're moving fast enough that relativistic effects start to become noticeable, though still minor. The trip to Andromeda would take about 253.7 million years. Still completely impossible for any human crew. Even with generation ships, where you're sending not just a crew but an entire population that reproduces during the journey. 253 million years is too long. Species evolve and go extinct on shorter timescales than that. Okay, let's push harder. What if we could travel at 10% the speed of light? This is starting to get into the realm of truly exotic propulsion systems. Nuclear pulse propulsion, where you're literally detonating nuclear bombs behind your spacecraft and riding the shockwave. Or perhaps a Bussard ramjet, a theoretical engine that scoops up hydrogen from interstellar space and uses it as fuel. At 10% light speed, the journey takes about 25.4 million years. Better, but still hopeless. Let's get really ambitious. 50% the speed of light. Now, we're in territory that might actually be theoretically possible, though we have no idea how to achieve it with current physics. At half-light speed, the trip takes about 5.1 million years. This is starting to approach something that might be survivable with generation ships. When your mission begins, your crew would need to understand that thousands of generations would live and die before arrival. The people who arrive would have no personal connection to Earth beyond abstract knowledge. They would have been born in space, lived their entire lives in space, and their great-great-great-grandparents, 1,000 generations back, would have been born in space. Earth would be mythology to them. At 90% the speed of light, the journey takes about 2.8 million years. Still impossibly long. At 99% the speed of light, you're down to about 2.6 million years. To actually make this journey in a single human lifetime, you'd need to travel at very close to the speed of light itself. Let's say 99.9999%. At this speed, thanks to time dilation, things get weird. From the perspective of someone on the spacecraft, moving at this incredible speed, time slows down dramatically relative to the universe outside. If you could maintain 99.9999% the speed of light, the subjective journey time for the crew might be only a few decades or even less, depending on how many nines you add. But here's the catch. From Earth's perspective, the journey still takes 2.5 million years. If you left Earth today, traveling at near light speed toward Andromeda, you might experience the trip as lasting only 20 or 30 years. You'd age normally, live a relatively normal life aboard the ship, and arrive at Andromeda still young. But Earth would have moved on without you. 2.5 million years would have passed. Humanity, as you knew it, would be gone. Our species might have evolved into something unrecognizable, or gone extinct, or spread throughout the galaxy, or transcended biology entirely. Your mission would be fundamentally one way, not because you can't return, but because there's nothing to return to. The Earth you left no longer exists. This is the temporal horror of interstellar travel at relativistic speeds. You can cheat your own experience of time, but you can't cheat the universe. The universe still ages at its normal rate. Even if the journey feels short to you, the rest of reality marches forward. But let's set aside the time problem for a moment and talk about the engineering challenges of actually building a ship that could make this journey. Because even if you solve the time problem, even if you're willing to accept that your ship's crew will be temporarily disconnected from the rest of humanity, you still have to build something that can survive the trip. And that's where things get truly terrifying. First, propulsion. How do you accelerate something to near light speed? The amount of energy required is staggering. Let's say you want to accelerate a spacecraft weighing 1,000 tons to 99% the speed of light. The kinetic energy of that spacecraft would be approximately equal to the total energy output of the Sun over several days. Where does that energy come from? Chemical rockets are completely inadequate. The best chemical rockets, like those used in the Saturn V, achieve exhaust velocities of around 1.6 miles per second. To reach near light speed, you'd need to carry so much fuel that the mass ratio becomes absurd. The rocket equation is merciless. As your desired speed increases, the amount of fuel you need grows exponentially. By the time you're talking about relativistic speeds, the fuel requirements become larger than planets. Nuclear propulsion helps, but not enough. Even fusion, which releases far more energy per unit mass than chemical reactions, still requires enormous fuel supplies for relativistic travel. One theoretical option is the photon rocket. You accelerate mass to the speed of light in the form of photons and use their momentum to push your ship forward. This is the most efficient rocket theoretically possible, but it still requires enormous amounts of energy, and the thrust is tiny. You'd need to run a photon drive for years just to reach a significant fraction of light speed. Another option is a laser sail. Build a massive laser array somewhere in the solar system, perhaps powered by the Sun itself. Point it at a spacecraft equipped with an enormous reflective sail. The pressure of the laser light pushing on the sail accelerates the spacecraft. This actually works, at least in theory. You're not limited by fuel mass because the energy source stays behind in the solar system. The breakthrough Starshot project has proposed exactly this for sending tiny probes to Alpha Centauri at about 20% the speed of light. But scaling this up to a crewed mission to Andromeda introduces new nightmares. The sail would need to be enormous, perhaps hundreds of miles across, yet incredibly thin and light to achieve a good acceleration. The laser array would need to be powerful, beyond anything we've ever built. And here's the problem. A laser sail can accelerate you up to speed, but it can't slow you down. Unless you plan to zip through Andromeda at 99% the speed of light without stopping, you need a way to decelerate at the destination. One option is a second laser array built at Andromeda, but that requires already having infrastructure there, which defeats the purpose of the first mission. Another option is to carry enough fuel to flip your ship around halfway through the journey and decelerate using a rocket engine. But now you're back to the fuel mass problem. Or perhaps you use the interstellar medium itself. A magnetic scoop could gather hydrogen from space as you travel, feeding it into a fusion reactor for deceleration fuel. But the densities of the interstellar medium are so low that you'd need a scoop thousands of miles across. Let's assume you solve propulsion somehow. You've built a ship, accelerated it to near light speed, and now it's cruising through the void toward Andromeda. What does the journey look like? The first major threat is radiation. Space is filled with cosmic rays, high-energy particles zipping through the void at relativistic speeds. When you're sitting still or moving slowly, cosmic rays are dangerous but manageable. You can shield against them with sufficient mass. But when you're moving at 99% the speed of light, you're not sitting still in the cosmic ray field. You're plowing through it. And due to something called relativistic beaming, particles that would normally hit you from all directions now appear to be coming almost entirely from directly ahead. From your perspective, The universe is blue shifted in front of you and red shifted behind you. Light and particles that were spread out across the sky are now concentrated into a narrow cone ahead of your ship. The cosmic microwave background, normally a faint glow at about 3 degrees above absolute zero, becomes intense radiation, cooking you from the front. Hydrogen atoms in the interstellar medium, normally sparse and mostly harmless, become deadly projectiles. At 99% light speed, a hydrogen atom has so much kinetic energy that it hits like a particle in a high-energy physics experiment. Every collision releases radiation. The front of your ship becomes a particle collider, constantly bombarded by interstellar hydrogen. Shielding helps, but it's not perfect. High-energy particles can create cascades of secondary radiation when they hit your shield. The shield itself becomes radioactive. The crew compartment would need to be deeply buried behind meters of shielding mass, adding to the spacecraft's weight and making the propulsion challenge even harder. Then there's the problem of interstellar dust. Space isn't empty. It's filled with microscopic dust grains, tiny particles of matter floating in the void. At normal speeds, these grains are harmless. At near light speed, they're bullets. A dust grain weighing a millionth of a gram, traveling at 99% the speed of light relative to your ship, carries the kinetic energy of a large bomb. If it hits your ship's hull, it would punch through like a meteor impact. You need protection. One option is a sacrificial shield, a massive block of ice or metal positioned ahead of the ship to absorb impacts. Dust grains hit the shield instead of your ship. The shield gradually erodes away during the journey. You'd need to carry enough shield mass to last the entire trip. Another option is active shielding. Powerful magnetic fields could deflect charged particles. Lasers could vaporize incoming dust grains before they reach the ship. But both of these require energy, and sustaining them for millions of years is a challenge. Even with perfect shielding, there's still the problem of navigation. At near light speed, you can't see where you're going in the normal sense. Light from objects ahead is blue shifted, compressed into a narrow cone. Light from objects to the side is aberrated, appearing to come from ahead. Your view of the universe becomes distorted. Everything in front of you appears brighter and more blue. Everything behind you fades and redshifts away. Steering becomes a challenge. If you need to avoid an obstacle, a rogue planet, or a dense dust cloud, you can't simply turn. At near light speed, changing direction requires enormous energy. Your turning radius is measured in light years. By the time you detect a hazard and begin to react, you might have already hit it. Pre-planning the route is essential. You'd need to map the space between here and Andromeda in exquisite detail before you leave, identifying hazards, planning course corrections, decades or centuries in advance. Now let's talk about the human element. Even if you solve all the physics and engineering problems, you still have to keep humans alive for the journey. If you're using time dilation to shorten the subjective journey, maybe the crew only experiences 30 or 40 years. That's manageable in principle. Humans have lived for decades in isolated environments before. Submarines' crews spend months underwater. Astronauts have spent years on the International Space Station. But the Andromeda ship would be different. There's no resupply. There's no emergency return to Earth. There's no contact with home because the light speed delay is millions of years. You send a message to Earth, and the response arrives 2.5 million years later. Effectively, you're alone, completely utterly alone. The psychological impact would be immense. Think about what isolation really means in this context. On Earth, even in the most remote locations, people know they're part of something larger. Antarctic researchers spend months at research stations, but they know there's a world beyond the ice. They know resupply missions are coming. They know their tour of duty has an end date. They can send emails, make phone calls, receive news from home. The isolation is real, but it's not absolute. On the Andromeda ship, isolation is total. The ship is your entire universe. Beyond the hull is vacuum, radiation, and 2.5 million light-years of nothing. No rescue is possible. No resupply is coming. No relief crew will arrive to give you a break. You're in a metal container, hurtling through space at near light speed, and that's your reality until you die or until you reach Andromeda. Studies of isolated groups show predictable patterns. Initially, there's excitement and novelty. Everyone's focused on the mission, working together, maintaining discipline. This honeymoon phase can last weeks or months. Then comes the adaptation phase. Routines are established, roles are clarified, the group settles into a rhythm. This is when small annoyances start to emerge. Someone's eating habits irritate others. Someone doesn't pull their weight on maintenance tasks. The same stories get told repeatedly until everyone's sick of hearing them. In normal isolation experiments, this is when conflicts emerge. But in those experiments, people know there's an end date. They can endure the annoyance because it's temporary. On the Andromeda ship, there is no end date. Not for decades. The person who annoys you now will be there tomorrow, next month, next year, for the rest of your life. You can't quit. You can't leave. You can't take a vacation from the people around you. This is your crew, your community, your entire social world, permanently. Psychologists call this group friction, and it's one of the biggest challenges in long-duration space missions. The ship would need to be designed with this in mind. Private spaces where crew members can retreat and be alone. Common areas large enough that people aren't constantly on top of each other. Work schedules that rotate people through different tasks and different groups to prevent stagnation. But there's only so much design can do. Eventually, personality conflicts will emerge. Romances will form and break apart. Friendships will be tested. The crew will need robust conflict resolution systems. Mediators trained in psychology. Perhaps even an AI counselor programmed to help manage interpersonal tensions. But here's the terrifying part. If someone becomes a serious problem, if they have a mental breakdown or become violent, or simply can't function anymore, there's nowhere to send them. In a prison, you can put someone in solitary confinement. On a submarine, you can confine them to quarters. On the International Space Station, in an emergency, you can send someone home. On the Andromeda ship, you can't do any of those things. The ship is too small for effective isolation. There's nowhere to send someone. You're stuck with them. The only option, in an extreme case, might be to put someone in cryogenic suspension or, in the worst-case scenario, make a decision no crew should ever have to make. And everyone aboard would know this. The pressure of that knowledge, the understanding that failure isn't an option, that you must make this work no matter what, would be crushing. Every crew member would need extraordinary emotional resilience. They'd need to be selected not just for technical skills, but for psychological stability. extensive testing before launch would be essential. Simulations of the isolation, the stress, the confinement. Only those who prove they can handle it should be selected. But even the best selection process can't predict everything. People change over time. Trauma that seemed manageable at launch might become overwhelming years into the journey. A crew member who seemed stable might develop psychological issues that weren't apparent during testing. The ship would need protocols for every contingency. What happens if a crew member becomes suicidal? What happens if violence breaks out? What happens if someone sabotages critical systems? These aren't pleasant scenarios to contemplate, but they're realistic possibilities on a multi-decade journey with no external support. Let's talk about the ship's design in more detail. To survive decades in space, moving at relativistic speeds, the ship would need to be unlike anything humanity has ever built. Size is the first consideration. The ship would need to be large, not just to carry fuel and supplies, but to provide adequate living space for the crew. Cramped quarters lead to psychological stress. Studies suggest each crew member would need at least 50 to 100 cubic meters of personal space. That's about the size of a small studio apartment. For a crew of 100, you're looking at 5,000 to 10,000 cubic meters just for living quarters. Add common areas, laboratories, workshops, medical facilities, storage, agricultural sections, and life support systems. And the ship might need to be hundreds of meters long. Perhaps a cylinder rotating for artificial gravity, like designs from the 1970s for space colonies. Rotation creates centrifugal force that simulates gravity. Walk on the inside of the cylinder's wall, and you feel pushed outward, which feels like being pulled down by gravity. The radius of the cylinder matters. Too small, and the rotation rate needs to be high, which can cause motion sickness. The gradient of artificial gravity from your head to your feet becomes noticeable and uncomfortable. Too large, and you need more structural mass to maintain integrity. A radius of 100 meters, rotating at about 2 rotations per minute, would create Earth-normal gravity at the rim. That's manageable, though some crew members might still experience nausea during the initial adjustment period. The structural challenge is immense. The cylinder needs to withstand the stress of rotation, while also serving as a radiation shield and a pressure vessel. Materials would need to be incredibly strong, yet as light as possible to minimize launch mass. Carbon composites, advanced alloys, perhaps even materials we haven't invented yet. Inside the cylinder, you'd need multiple redundant systems for everything: life support, power generation, navigation, communications. If a critical system fails and you can't repair it, the mission is over. Everyone perishes. Redundancy is the only insurance against catastrophic failure. At least 2 of everything, preferably 3. Multiple oxygen generation systems, multiple water recycling loops, multiple power sources. The ship would likely use nuclear reactors for power. Solar panels are useless once you leave the solar system. Sunlight drops off with the square of distance. By the time you're even a fraction of the way to Andromeda, solar power provides essentially nothing. Nuclear fission reactors are proven technology. We've used them on Earth for decades, and they've powered some spacecraft and submarines. A fission reactor could run for decades with proper maintenance and fuel management. But nuclear fuel is heavy, and it's radioactive even before it's used. Shielding the reactor to protect the crew adds more mass. And spent fuel remains dangerously radioactive for thousands of years. You'd need secure storage for waste, isolated from the crew compartments. Fusion reactors would be better, if we can ever make them work reliably. Fusion produces more energy per unit mass of fuel and generates less radioactive waste. But despite decades of research, we still don't have a working fusion reactor that produces more energy than it consumes. Maybe by the time we're ready to attempt an Andromeda mission, we'll have cracked fusion. If not, we're stuck with fission, with all its limitations. Power requirements would be substantial. Life support systems consume energy continuously. Air circulation, temperature control, water purification, waste processing, all of it requires power. The agricultural systems need light for the plants. Computers and navigation systems run constantly. Communication systems, though largely useless given the distance to Earth, would still need to operate for internal ship functions and potential communication with other ships or probes. You might need 10 to 20 megawatts of continuous power. That's about the output of a small nuclear submarine reactor running non-stop for decades. Maintaining the reactors would be a critical ongoing task. The crew would need trained nuclear engineers who understand the systems intimately. Parts would wear out and need replacement. The ship would carry spare components, but only a finite supply. If something breaks that you can't replace, you'd need to fabricate the part using onboard manufacturing. 3D printers, machine shops, raw materials. The ship would need to be partially self-sufficient, capable of producing at least some of its own replacement parts. This adds to the complexity. Now, you need manufacturing equipment, raw materials, crew members trained in fabrication and engineering. The more self-sufficient the ship is, the heavier it becomes, and the harder it is to accelerate to relativistic speeds. There's a balance between carrying everything you need and keeping mass low enough to reach your destination. And then there's the question of what happens when something goes wrong that you can't fix. Let's say a critical reactor component fails, and you don't have a spare, and you can't manufacture one. Power output drops. You have to start rationing electricity. Non-essential systems get shut down. Maybe you reduce the artificial gravity by slowing the rotation. Maybe you dim the lights, lower the temperature, reduce air circulation. The crew's quality of life deteriorates. If power drops low enough, you might not be able to maintain the agricultural systems. Food production declines. Rationing becomes necessary. In the worst case, you might need to put some crew members into cryogenic suspension to reduce the number of people consuming resources. But cryogenic suspension has its own risks. Freezing and thawing biological tissue without causing damage is extremely difficult. Ice crystals form inside cells, rupturing membranes, destroying structure. Current cryonics technology uses chemicals called cryoprotectants to prevent ice formation, essentially turning the body into a glass-like state. But this process is toxic at normal temperatures. You need to perfuse the entire body with cryoprotectants, then cool it rapidly to prevent ice formation, then store it at extremely low temperatures for the duration of the suspension. And when you thaw, you need to reverse the process, warming carefully, flushing out the cryoprotectants, restarting metabolism. Every step has risks. Brain damage from inadequate perfusion, cellular damage from recrystallization during thawing, organ failure when metabolism restarts. We've successfully frozen and thawed small organisms, certain types of cells, even some simple tissues. But whole humans? That's still science fiction. By the time we're building Andromeda ships, maybe we'll have perfected it. Or maybe not. If cryogenic suspension doesn't work reliably, the crew is awake for the entire journey. Decades of consciousness, confined to the ship, with all the psychological challenges that entails. Let's talk about food in more detail, because it's one of the most challenging aspects of the mission. An adult human needs about 2,000 to 2,500 calories per day. That's roughly 1 kilogram of food, depending on the nutritional density. For a crew of 100 over 30 years, you'd need about 11 million kilograms of food. That's 11,000 metric tons. No ship can carry that much mass. Even if you could, storing it for 30 years without spoilage would be impossible. So, you grow food aboard the ship. Hydroponics seems like the obvious choice. Plants grown in nutrient-rich water under artificial light in controlled conditions. No soil needed, which saves mass. Water can be recycled. Plant waste can be composted or broken down into nutrients. But hydroponics at the scale needed for 100 people is an enormous undertaking. You'd need growing space, lighting, nutrient management, pest control, pollination for certain crops. And diversity is important. You can't just grow one crop. Humans need a varied diet for proper nutrition. Vitamins, minerals, proteins, fats, carbohydrates, fiber. You'd need multiple species of plants. Grains like wheat or rice for carbohydrates. Legumes like beans or lentils for protein. Leafy greens for vitamins and minerals. Fruits for additional vitamins and variety. Perhaps potatoes or sweet potatoes for calorie density. Each crop has different growing requirements. Different light spectra, different nutrient concentrations, different temperature ranges. Managing all of this in a closed environment is complex. Then there's the question of protein. Plants provide some protein, but complete proteins with all essential amino acids are harder to get from plants alone. You might supplement with insects. Crickets, mealworms, other arthropods can be raised in small spaces, convert plant matter into protein efficiently, and provide complete nutrition. Many cultures on Earth already eat insects regularly. For a space mission, it's a practical choice. Or maybe you use cultured meat, growing animal cells in bioreactors without raising actual animals. This technology is still in development, but it holds promise. You could produce beef, chicken, fish, all from cell cultures, without the space and resource requirements of live animals. But bioreactors need careful management. Contamination can ruin entire batches. The nutrient media needs to be sterile and precisely formulated. It's another system that can fail. Another point of vulnerability. Water is perhaps the most critical resource. Humans need about 2 to 3 liters per day for drinking. More for cooking, cleaning, hygiene. Agricultural systems need water for the plants. Cooling systems might use water as a heat transfer medium. In total, you might need hundreds of liters per person per day. For 100 people, that's tens of thousands of liters daily. Over 30 years, you're talking about hundreds of millions of liters. Obviously, you can't carry that much water. You recycle. Every drop of water is precious. Wastewater from sinks, showers, and toilets gets filtered, purified, and returned to the potable water supply. Humidity in the air is captured by dehumidifiers and recycled. Even urine and sweat are processed and purified. The technology exists. The International Space Station recycles about 93% of water. But that 7% loss adds up. Over 30 years, even small losses mean you'd run out eventually. The Andromeda ship would need to push recycling efficiency even higher. 99% recovery or better. That requires advanced filtration, careful monitoring, and acceptance that the water you're drinking today was someone's urine last week. It's psychologically challenging for some people, but it's the only way to make the mission viable. Air is another critical resource. Humans breathe in oxygen and exhale carbon dioxide. Plants do the opposite during photosynthesis, consuming carbon dioxide and producing oxygen. In theory, a closed ecosystem with the right balance of plants and humans would be self-sustaining. The plants produce the oxygen the humans need, and the humans produce the carbon dioxide the plants need. In practice, balancing this is difficult. Plants don't produce oxygen at a constant rate. It varies with light levels, growth stage, and plant health. Humans don't consume oxygen at a constant rate either. Physical activity increases oxygen demand. You need buffer systems, reserves of oxygen, and carbon dioxide scrubbers to handle fluctuations. Chemical scrubbers can remove carbon dioxide from the air, but they consume the carbon dioxide permanently. It's lost unless you regenerate it, which requires energy. Better to use biological systems where possible. Plants, algae, photosynthetic bacteria. These organisms can close the loop, recycling carbon dioxide back into oxygen. But they need light, nutrients, and careful management. If your agricultural systems fail, if a disease wipes out your plants, or a power failure kills your algae tanks, you lose your oxygen production. You'd fall back on chemical systems and stored reserves, but those are finite. Once they're gone, the crew suffocates. Redundancy is essential. Multiple independent oxygen production systems. Stored oxygen reserves as backup. Emergency protocols if oxygen levels drop. Every crew member would need to understand the life support systems and be able to perform basic maintenance. Because if the oxygen system fails and nobody can fix it, everyone perishes in a matter of hours or days. The stakes are absolute. There's no margin for error. Every system must work, every backup must be functional, every crew member must perform their role. Failure means death, not just for individuals, but for the entire mission. The pressure of living under those conditions, day after day, year after year, would be immense. Let's talk about what the crew experiences during the journey. Time dilation at 99.9999%. The speed of light is extreme. From the crew's perspective, the journey might take only 20 to 30 years. They age normally, experience time normally, but the universe outside ages much faster. When they left Earth, they said goodbye to family and friends. Those people are now gone, dust, for millions of years. The Earth they knew, with its cities and cultures and technologies, has been transformed beyond recognition, or perhaps destroyed entirely. They'll never know. By the time a message from the ship could reach Earth, and a response could return, millions of years would pass. Effectively, the ship is isolated not just in space but in time. They've jumped forward millions of years into the future, bypassing everything that happened in between. Every empire that rose and fell, every species that evolved and went extinct, every discovery and invention, all of it invisible to them. They left Earth in the 21st century and will arrive in Andromeda in the era corresponding to what, from Earth's perspective, is millions of years in the future. But subjectively, for them, only a few decades passed. This creates a profound disconnect. The crew members know intellectually that time is passing differently for them versus the rest of the universe. But experiencing it is different from knowing it. When they look out the windows, if the ship has windows, they see the universe blue shifted ahead and red shifted behind. Stars appear distorted, compressed into a cone of light in front of the ship. The cosmic microwave background, normally invisible, might be boosted into visible light by the Doppler shift. The view would be alien, beautiful, and terrifying. A reminder that they're traveling at speeds nothing biological was meant to experience. The faster you go, the more extreme the effects become. At these speeds, even tiny particles become dangerous. The ship's forward shield is constantly being bombarded, eroding away molecule by molecule. The crew would need to monitor the shield's thickness, potentially adding mass to it during the journey if possible, or accepting that the shield will eventually fail and hoping they reach Andromeda before that happens. Navigation becomes critical. At near light speed, you're covering vast distances quickly. In 1 year of ship time, traveling at 99.9999% the speed of light, you cover almost 1 light year of space. From Earth's perspective, you're covering 1 light year per year because you're traveling at nearly light speed. But from the crew's perspective, time is dilated, so they experience much less than a year passing. This means they need to know exactly where they're going and exactly how to get there. Course corrections at these speeds are difficult. Turning requires enormous energy. Firing thrusters to change direction means accelerating mass, and at relativistic speeds, mass increases. The faster you're going, the more energy you need to change your velocity. Small course corrections early in the journey are feasible. Large maneuvers late in the journey might be impossible. So, the initial trajectory needs to be precise. You aim for a specific region of Andromeda. Calculate the trajectory accounting for Andromeda's motion through space, accounting for the curvature of space-time caused by intervening mass, accounting for everything. And you commit. Once you're at speed, you're locked in. If you aimed wrong, if your calculations were off, you might miss Andromeda entirely. Or arrive in the wrong part of the galaxy, far from any useful stars or resources. The ship would carry telescopes to observe the destination as it approaches. Over the decades of the journey, Andromeda would grow larger in the viewports. At first, it's a faint smudge, barely distinguishable from the distorted star field. Then, it starts to resolve into a disk. Individual bright regions become visible, star-forming regions glowing with the light of young, massive stars. Dust lanes threading through the spiral arms become apparent. Eventually, individual stars might be resolvable, though the blue shift would make everything appear strange and color-shifted. The crew would be watching, analyzing, searching for suitable destinations within the galaxy. A star system with a yellow sun similar to ours. A planet in the habitable zone. Signs of water, oxygen, conditions that might support life, or at least support a human colony. They'd be picking their landing site, or rather their arrival site, years in advance. And they'd be preparing for deceleration. This is where things get technically nightmarish. To slow down from 99.9999%, the speed of light takes as much energy as it took to accelerate to that speed in the first place. If you used a laser sail to accelerate, you can't use it to decelerate. The laser is back at Earth, millions of light years behind you. You need a different method. One option is to flip the ship around and use a rocket engine to thrust against your direction of motion. But this requires carrying fuel, lots of fuel. The Tsiolkovsky rocket equation is merciless. To achieve a given change in velocity, you need an exponential amount of fuel. For relativistic speeds, the fuel requirements become absurd. You'd need to carry more fuel than the mass of planets. Unless you use something incredibly efficient, like a photon rocket or an antimatter engine, antimatter annihilates with matter, converting mass directly into energy with 100% efficiency. It's the most powerful fuel theoretically possible. A few kilograms of antimatter could provide enough energy to decelerate a large spacecraft. But producing antimatter is another challenge. Currently, we can create tiny amounts in particle accelerators, fractions of a microgram. Scaling that up to kilograms would require technology far beyond what we have. And storing antimatter is dangerous. If it touches normal matter, it annihilates instantly, releasing energy. You need magnetic containment, keeping the antimatter suspended in a vacuum, never touching the walls of the container. Any containment failure would be catastrophic. The entire fuel supply would detonate, vaporizing the ship. But let's assume you solve this. You've carried enough antimatter to decelerate. You flip the ship around, aim the engine forward, and start firing. The antimatter reacts with regular matter, producing gamma rays and high-energy particles. These are directed out the back of the engine, providing thrust in the opposite direction of your motion. Slowly, over months or years, your speed decreases. The blue shift ahead starts to lessen. The universe starts to look more normal. Andromeda, which was a compressed disk of light ahead, begins to spread out, filling more of the sky. Individual stars become distinguishable. You're arriving. After decades of travel, after sacrificing everything, after crossing 2.5 million light-years of space, you're finally here. You're in Andromeda. The ship's velocity drops below relativistic speeds. Time dilation effects fade. Your personal time and the universe's time start to align again. You're moving slowly enough now that orbital mechanics apply. You can maneuver, change course, navigate to your chosen destination. Ahead of you, a star system. A yellow dwarf star, similar to the Sun. Planets orbiting it, detected from afar by the wobble they induce in the star's motion and the dips in brightness as they transit across its face. One of those planets is in the habitable zone. Spectroscopy from the ship's instruments shows water vapor in the atmosphere, oxygen, possibly even chlorophyll signatures, suggesting plant life, or perhaps nothing. A barren rock, devoid of life, but with the basic ingredients needed to support a human colony. Either way, it's your destination. The ship approaches, enters orbit around the planet. After 30 years of travel, the crew steps onto a new world. They breathe air that didn't come from a recycling system. They feel natural gravity, not the artificial spin of the ship. They see a sky filled with unfamiliar stars. The Milky Way is visible, a faint smudge in the night sky, 2.5 million light-years away. Somewhere in that smudge is Earth, unimaginably distant. The crew is home, but it's a new home. A world in Andromeda. they'll never see Earth again. They'll never know what happened there, whether humanity thrived or perished, whether the species spread to the stars or stayed confined to one planet. All of that is lost to them, separated by millions of years and millions of light years. They're on their own now. They have the knowledge and technology they brought with them. They have each other. And they have this new world. What they do next depends on what they find. If the planet is habitable, they start building. Shelters, greenhouses, power systems. They extract resources from the planet, mine metals, refine materials, construct infrastructure. The ship that brought them becomes a resource. Parts are scavenged, repurposed. The nuclear reactors provide power for the colony. The hydroponic systems are expanded using local materials. Over time, the colony grows. Children are born, the first generation of humans born in Andromeda. They grow up under alien skies, learning about Earth from stories and recordings, but never experiencing it. To them, Earth is mythology. Andromeda is reality. They're Andromedans, not humans from Earth. Or maybe the planet isn't habitable. Maybe the atmosphere is toxic, the surface too cold or too hot, the conditions incompatible with human life. The crew would need to stay in the ship or build habitats, sealed environments where they can survive. Mining the planet for resources, extracting water from ice deposits, splitting it into hydrogen and oxygen for fuel and breathing. Living in bubbles on an alien world, isolated, struggling to survive. This is the gamble of the journey. You travel for decades based on observations made from 2.5 million light years away. You hope the destination is what you think it is, but you won't know for sure until you arrive. And by then, it's too late to change your mind. Let's talk about what they might encounter. Is Andromeda inhabited? The galaxy contains 1 trillion stars. Statistically, some of those stars likely host planets. Some of those planets are probably inhabitable zones. And on some of those planets, life may have emerged. If even a tiny fraction of planets develop life, and a tiny fraction of those develop intelligent life, Andromeda could be teeming with civilizations. Or it could be empty. The Fermi paradox applies here. If intelligent life is common, why haven't we detected any signs of it? Maybe life is rare. Maybe intelligence is even rarer. Maybe civilizations tend to destroy themselves before they can spread to other stars. Or maybe they're out there, but we haven't looked in the right way or the right place. The crew of the Andromeda ship might be the first to answer this question. If they encounter evidence of alien life, it would be one of the most significant discoveries in history. But would they recognize it? Life on Earth is based on carbon chemistry, water as a solvent, DNA as the information storage molecule. But life elsewhere might be fundamentally different. Silicon-based instead of carbon-based. Using ammonia instead of water. Storing information in something other than DNA. We might not recognize it as life at all. Or we might recognize it, but be unable to communicate with it. If intelligence evolved in a radically different environment, under different selection pressures, it might think in ways completely alien to us. Our concepts of language, mathematics, logic might not translate. Or maybe we'd find ruins. Evidence that a civilization existed millions of years ago, but is now gone. Ancient structures, artifacts, technology left behind by a species that perished. This would be haunting. A reminder that intelligence doesn't guarantee survival, that even advanced civilizations can fail. The crew might explore these ruins, trying to understand what happened, learning from the mistakes of the beings that came before. Or maybe they'd find an active civilization, beings that evolved in Andromeda, perhaps at a similar technological level to humans or far more advanced. First contact with an alien intelligence. How would it go? Would they be peaceful, curious, welcoming? Would they see humans as equals, as primitives, as threats? Would communication even be possible? The scenarios are endless, and none of them can be predicted. We have no frame of reference for how alien minds might work. Our only example of intelligence is ourselves, and we're hardly unified or consistent in our behavior. The crew would need protocols for contact, guidelines for how to approach, how to communicate, how to respond to aggression or confusion. But those protocols would be based on speculation, not experience. They'd be making it up as they go, hoping they don't inadvertently trigger a conflict or misunderstanding that ends in disaster. And here's another terrifying possibility. What if the aliens are hostile? What if the crew arrives in Andromeda, begins establishing a colony, and attracts the attention of a species that sees them as invaders? The crew is isolated, 2.5 million light-years from any help. They have the technology they brought with them, but nothing more. If they encounter a hostile civilization with superior technology, they'd be helpless. Their only option would be to flee. But where would they go? They've already traveled 2.5 million light-years. They don't have the fuel or resources to travel that distance again. They're stuck in Andromeda, for better or worse. This is the ultimate vulnerability of interstellar colonization. You're betting everything on the hope that the destination is safe, that you won't encounter something you can't handle, and you won't know until you arrive. But let's consider a more optimistic scenario. The crew arrives, finds a habitable world, encounters no intelligent life, and begins building a colony. Over generations, the colony grows. More habitats are constructed, more land is cultivated, more resources are extracted. The population increases. Children grow up, have children of their own. The colony becomes self-sustaining, no longer dependent on the ship or the technology brought from Earth. They develop their own culture, their own identity. They're no longer humans from Earth. They're Andromedans. They remember Earth, but it's a distant memory, a historical curiosity. Their lives are here, in this new galaxy. Over centuries, they might spread to other stars in Andromeda, building ships of their own, exploring nearby systems, establishing new colonies. The process that brought them to Andromeda repeats on a smaller scale within the galaxy. Eventually, Andromeda could be filled with human colonies. Millions of worlds, trillions of people, all descended from the original crew of the first Andromeda ship. A new branch of humanity, separated from Earth by time and distance, evolving independently. And here's a strange thought. If the ship left Earth in the 21st century and traveled at near light speed, experiencing only 30 years of subjective time, the crew would arrive in what, from Earth's perspective, is 2.5 million years in the future. But what if humanity on Earth also developed interstellar travel? What if, over the millions of years that passed from Earth's perspective, humans spread throughout the Milky Way, developed new technologies, perhaps even found ways to travel faster than light, Or bypass the light speed limit through wormholes or other exotic means? By the time the Andromeda ship arrives, Earth-based humans might have already reached Andromeda through other methods. The crew would arrive expecting to be pioneers, only to find that they're late to the party. Andromeda is already colonized by their distant descendants from Earth, humans who evolved over millions of years, who might be so different that they're no longer recognizable as the same species. The crew would be relics, fossils from an earlier era of humanity. Or perhaps Earth's humanity went extinct. Wars, environmental collapse, asteroid impacts, any number of catastrophes could have wiped out the species. The crew of the Andromeda ship would be the last humans, carrying the species into a new galaxy, unaware that their homeworld is dead. They'd be the sole survivors, responsible for ensuring that humanity continues. The weight of that responsibility would be crushing. Every decision they make, every policy they implement, shapes the future of the species. If they fail, if the colony collapses, humanity ends. There are no other humans left anywhere in the universe. Just them. This is the existential burden of interstellar colonization. You're not just exploring. You're carrying the torch of your species into the unknown. And if you drop that torch, it goes out forever. Let's zoom out and consider the broader implications. Why would humanity attempt a journey to Andromeda? What drives a species to undertake something so difficult, so dangerous, so uncertain? Part of it is survival. If Earth becomes uninhabitable, whether through natural disasters, human-caused catastrophes, or the eventual expansion of the Sun into a red giant, humanity needs a backup. Colonizing other planets, other star systems, ensures that the species survives, even if Earth doesn't. Andromeda represents the ultimate backup. If something catastrophic happens in the Milky Way, a gamma-ray burst, sterilizing large regions of the galaxy, a collision with another galaxy disrupting star systems, humans in Andromeda would be safe. They're separated by 2.5 million light-years. Nothing that happens in the Milky Way could threaten them. But survival isn't the only motivation. There's also curiosity. Humans are explorers by nature. We've always pushed beyond the known, seeking new horizons. From the first humans leaving Africa, to Polynesians crossing the Pacific, to astronauts landing on the moon, exploration is part of who we are. Andromeda is the ultimate frontier. The farthest destination we can see with our naked eyes. Reaching it would be the greatest achievement in human history. It would prove that there are no limits to where we can go, no boundaries we can't cross. And there's a philosophical dimension. Reaching Andromeda would mean that humanity is no longer confined to one galaxy. We'd be a multi-galactic species. Our presence would span 2 galaxies, 2 distinct regions of the universe. That's a profound shift in perspective. It means we're not just residents of the Milky Way. We're residents of the universe itself. We belong everywhere. But all of this assumes we can actually do it. And that's far from certain. The challenges are immense. The energy requirements, the technological hurdles, the human factors, all of it pushes against the boundaries of what's possible. Maybe we'll never attempt it. Maybe the journey to Andromeda will remain forever in the realm of science fiction. A dream that's too ambitious, too expensive, too dangerous to ever become reality. Or maybe we will. Maybe future generations will look at the challenges and decide they're worth overcoming. Maybe they'll develop the technology, build the ships, recruit the crews, and launch. And maybe, thousands of years from now, humans will walk on worlds in Andromeda, looking up at the night sky and seeing the Milky Way as a distant smudge of light. A reminder of where they came from. A testament to the journey they undertook. There's something deeply moving about that possibility. The idea that humanity could reach so far, achieve so much, overcome so many obstacles. It speaks to our resilience, our ingenuity, our refusal to accept limits. But it also highlights our fragility, how small we are in the cosmic scheme, how dependent on technology, on planning, on luck. One mistake, one failure, one unforeseen catastrophe, and the mission ends. The crew perishes. The dream dies. The journey to Andromeda is a mirror. It reflects both our greatest strengths and our deepest vulnerabilities, our ambition and our limitations, our courage and our fear. When we look at Andromeda in the night sky, we're not just seeing a distant galaxy. We're seeing a challenge, a question posed by the universe. Can you reach me? And we don't know the answer yet. Maybe someday we will. But to understand just how profound this challenge is, we need to dive deeper into the physics of what we're attempting. Let's talk about energy in concrete terms. The kinetic energy of an object is 1/2 its mass times its velocity squared. That's the classical formula, and it works fine for slow speeds. But at relativistic speeds, you need to use Einstein's equations. The energy of a moving object approaches infinity as its speed approaches the speed of light. This is why nothing with mass can reach light speed. It would require infinite energy. For our Andromeda ship, let's say it weighs 10,000 tons. That's roughly the mass of a large naval ship. To accelerate this to 99% the speed of light, you need about 900,000 times the total energy humanity currently produces in an entire year. That's the energy output of the sun for several hours, concentrated into accelerating a single ship. Where does this energy come from? If you're using conventional rockets, you'd need fuel with an exhaust velocity approaching the speed of light. Only matter, antimatter annihilation, or direct photon rockets achieve this. And you'd need a lot of it. The Tsiolkovsky rocket equation tells us that to reach a given final velocity, you need an initial mass ratio that's exponential in the velocity change divided by the exhaust velocity. For relativistic velocities, with even the best possible exhaust velocity, the mass ratios become astronomical. You'd need a fuel mass millions of times larger than the payload mass. A ship weighing 10,000 tons would need billions of tons of fuel. That's more than Mount Everest. You can't build that. Even if you could, accelerating that much mass would require even more energy, creating a recursive problem. This is why laser sails and other external propulsion methods are attractive. The energy source stays behind. You're not carrying the fuel mass with you. But then you have the problem of deceleration, as we discussed. One theoretical solution is the magnetic sail for deceleration. As you approach Andromeda, you deploy an enormous magnetic field. This field interacts with the interstellar medium, the sparse gas and plasma between stars. Charged particles in the interstellar medium push against the magnetic field, creating drag. Over time, this drag slows you down. The advantage is you don't need to carry deceleration fuel. The disadvantage is it's slow. The interstellar medium is incredibly sparse. A few atoms per cubic centimeter. The drag force is tiny. It might take decades or centuries to decelerate from near light speed to a manageable velocity. By the time you've slowed down enough to enter orbit around a planet, another generation or two might have passed. The mission timeline extends further. Another option is gravitational assist, using the gravity of massive objects to change your velocity. Spacecraft do this routinely in the solar system, flying past planets to gain or lose speed. In Andromeda, you could fly past a massive star or even a black hole, using its gravity to bend your trajectory and slow down. But this requires precise navigation. You need to know exactly where these massive objects are, plot a course that takes you close enough to get the assist, but not so close that tidal forces tear your ship apart. And gravitational assists only work if there's a suitable massive object positioned where you need it. You can't move stars or black holes. You're at the mercy of whatever's actually there. Let's consider the journey from another angle, the sheer duration. Even with time dilation shortening the subjective experience for the crew, the objective time is still 2.5 million years. To put that in perspective, 2.5 million years ago, the Earth was in the midst of the Quaternary glaciation period. Ice ages were beginning. Early hominins were spreading across Africa. Homo habilis was alive, making simple stone tools. Our species, Homo sapiens, wouldn't appear for another 2 million years. If you had left Earth 2.5 million years ago traveling toward Andromeda, you'd be arriving just about now. And in that time, on Earth, our entire species evolved. From pre-human ancestors to modern humans. From stone tools to spacecraft. From hunter-gatherers to global civilization. Everything we consider human history, all of recorded civilization, spans only about 10,000 years. The journey to Andromeda is 250 times longer. It's a timescale so vast that it dwarfs not just individual human lives, but the entire history of our species. This has profound implications for the mission. Any ship you send, any technology you use, any plan you make, is based on the knowledge and capabilities of the present moment. But by the time the ship arrives, the Earth from which it launched will have changed beyond recognition. If Earth-based humanity continues to advance technologically, they might develop faster propulsion methods. They might send a second ship that leaves Earth 1 million years after the first ship, but arrives at Andromeda earlier because it's traveling faster. The first crew would encounter the second crew's descendants, already established in Andromeda. This is called the weight calculation. If technology is improving, is it better to send a ship now with current technology, or wait until technology improves and send a faster ship later? The faster ship might arrive first, making the slow ship's journey pointless. But if you wait too long, you might never send a ship at all. There's always a newer, better technology just over the horizon. At some point, you have to commit. You have to say, this is the technology we have, this is the ship we can build, and we're going to launch it, knowing that it might be obsolete by the time it arrives. This is a decision with no right answer. It depends on your time horizon, your risk tolerance, your goals. Some argue that we should send ships now, with whatever technology we have, because waiting might mean never going. Others argue that we should invest in research, develop better propulsion, better life support, better everything, and only launch when we're truly ready. Both positions have merit. Both have risks. Let's talk about historical parallels. Human exploration has always pushed beyond the known. The Polynesians crossed thousands of miles of open ocean in outrigger canoes, navigating by stars and wave patterns, seeking new islands. Many expeditions failed. Canoes were lost at sea. Crews perished. Entire populations sometimes vanished. But some succeeded. They found new islands, established colonies, and over generations populated the Pacific. The European age of exploration saw ships sailing around the world, discovering new continents, mapping coastlines. Ferdinand Magellan's expedition to circumnavigate the globe began with 5 ships and 270 men. Only one ship returned, carrying 18 survivors. Magellan himself perished in the Philippines. But the expedition succeeded in proving the Earth could be circumnavigated, opening up new trade routes and expanding human knowledge. The Antarctic expeditions of the early 20th century saw explorers venturing into one of Earth's most hostile environments. Robert Falcon Scott's expedition to the South Pole in 1911 ended in tragedy. Scott and his team reached the pole, only to find that Roald Amundsen had beaten them there. On the return journey, they encountered blizzards and extreme cold. All 5 members of the Polar Party perished. Their frozen bodies were found months later. But their sacrifice wasn't meaningless. The scientific data they collected, the samples they gathered, contributed to our understanding of Antarctica and Earth's climate. The space age brought new kinds of exploration. The Apollo missions to the moon were triumphs of engineering and courage. But they were also dangerous. Apollo 1 ended in fire during a ground test, taking the lives of 3 astronauts. Apollo 13 suffered an oxygen tank explosion en route to the moon, nearly stranding the crew in space. They survived only through ingenuity and teamwork, nursing a crippled spacecraft back to Earth. The journey to Andromeda would be the ultimate exploration. Far more dangerous than crossing an ocean, more isolating than Antarctica, more uncertain than the moon landings. The crew would be venturing into an environment we've never tested, using technology we've never fully proven, on a timescale that exceeds any human endeavor. The risks are enormous. The chances of success are uncertain. But that's the nature of exploration. You go because it's difficult, because it's never been done. Because the potential rewards, both tangible and intangible, justify the risks. Or at least, that's the argument. But we should also consider the counter-argument. Maybe the journey to Andromeda is too risky, too expensive, too uncertain to ever justify. Maybe the resources required would be better spent elsewhere. Solving problems on Earth, colonizing the solar system, developing sustainable technologies. The energy needed to send one ship to Andromeda could power entire civilizations for generations. The materials could build habitats for billions of people. The scientific talent required to design and operate the mission could solve countless other challenges. Is it ethical to commit such resources to a project that benefits so few? The crew of the Andromeda ship might number in the hundreds at most. Meanwhile, billions of people on Earth might be struggling with poverty, disease, environmental degradation. Should we prioritize exploration or improvement of conditions at home? There's no easy answer. Throughout history, societies have grappled with this tension: exploration and discovery versus domestic needs. Investment in the future versus addressing present problems. Often, the answer is to do both. Exploration doesn't necessarily come at the expense of domestic improvement. The technologies developed for space missions often have applications on Earth. The Apollo program drove advances in computing, materials, science, and telecommunications. GPS satellites, originally developed for military navigation, now underpin global commerce and communication. Research into closed-loop life support systems for spacecraft informs sustainable agriculture and water management on Earth. Maybe the same would be true for an Andromeda mission. The technologies required, propulsion, energy generation, biological recycling, might have terrestrial applications that benefit everyone. Or maybe not. Maybe interstellar travel is so specialized that the research doesn't transfer. It's an open question. But beyond the practical considerations, there's a philosophical dimension. Humanity is defined, in part, by our curiosity, our drive to explore, to understand, to reach beyond our current limits. If we abandon that drive, if we decide that Andromeda is too far, too hard, too risky, what does that say about us as a species? Does it mean we've matured, become more pragmatic, more focused on achievable goals? Or does it mean we've lost something essential, some spark of ambition that makes us human? Again, there's no right answer. Different people will weigh these considerations differently. Some will see the journey to Andromeda as a noble aspiration, a goal worth pursuing regardless of the cost. Others will see it as folly, a waste of resources on an impossible dream. Both perspectives have validity. What's important is that we think carefully about what we value and why. Now, let's consider one more aspect of the journey: the message it sends. If humanity builds a ship and sends it to Andromeda, that act itself communicates something. It says we're here, we're capable, we refuse to be confined. Even if the ship never arrives, even if it's lost in the void, the attempt matters. It's a statement of intent, a declaration that we're a species that reaches for the stars. And if the ship does arrive, if the crew establishes a colony, that's a message to the universe. Humanity has left its birth galaxy. We've crossed the intergalactic void. We're multigalactic. That's a profound achievement. It places us in a category of civilizations that have mastered interstellar and intergalactic travel. If there are other intelligences out there, they would recognize this as a significant milestone, a sign that humanity has reached a certain level of technological and organizational capability. But it's also a message to ourselves, a reminder that we can accomplish extraordinary things when we work together, when we commit to a shared goal, when we're willing to sacrifice for a vision larger than our individual lives. The crew of the Andromeda ship would be heroes, not in the traditional sense of warriors or conquerors, but as pioneers. People who ventured into the unknown for the benefit of all humanity. Their names would be remembered for as long as our species exists. They would be the first humans to leave the Milky Way, the first to reach another galaxy, the first to establish humanity's presence in Andromeda. That's a legacy worth considering. But it comes with a cost paid by the crew members who leave everything behind, a cost paid by society in terms of resources devoted to the mission, a cost in terms of risk and uncertainty. Whether that cost is justified depends on what we value. If we value exploration for its own sake, if we believe that humanity's destiny lies among the stars, then yes, the journey is worth it. If we value stability, safety, and focusing on present needs over distant dreams, then maybe not. There's no objective way to resolve this. It's a question of values, of priorities, of what kind of species we want to be. Let's bring this back to the personal level. Imagine you're offered a place on the Andromeda mission. You'd be leaving Earth forever. Everyone you know, everyone you love, would be gone by the time you arrived. You'd experience only 30 years of the journey subjectively, but you'd never return. Andromeda would be your new home. Would you go? Some people would say yes immediately. The adventure, the discovery, the chance to be part of history would be irresistible. They'd see it as the opportunity of a lifetime, or rather, the opportunity of all lifetimes. To see things no human has ever seen, to walk on worlds in another galaxy, to be a pioneer in the truest sense. Others would say no just as quickly. The sacrifice is too great. Leaving behind family, friends, Earth itself, forever. Never seeing home again, never knowing what happens to the people and places you love. The isolation, the risk, the uncertainty would be unbearable. And many people would be conflicted, drawn to the adventure but terrified of the cost, wanting to go but unable to leave behind what they have. This is the human dimension of the journey. It's not just about physics and engineering. It's about people making choices that will define the rest of their lives. The crew selection process would be intense. Psychological screening to identify people with the right temperament, training to prepare them for the challenges. Time to say goodbye, to make peace with their decision. And even after all that, some crew members might change their minds, might realize during the journey that they made a mistake, that the cost was higher than they anticipated. But there's no turning back. Once you're launched, you're committed. The mission continues, regardless of individual doubts or regrets. This is the terrifying finality of the journey. You make a choice, and then you live with it for the rest of your life. There's no second guessing, no changing course, no going home. You're all in permanently. That level of commitment is almost unimaginable in our modern world. We're used to flexibility, to keeping options open, to changing our minds. The Andromeda journey offers none of that. It demands absolute commitment. And that might be the most terrifying aspect of all. Not the radiation, not the isolation, not the technical challenges, but the psychological weight of a decision that can never be undone. A choice that determines the entire trajectory of your life and removes all other possibilities forever. How do you make a decision like that? How do you know if you're ready? The honest answer is, you don't. You can prepare, you can train, you can think it through from every angle. But ultimately, you're stepping into the unknown. You're betting your life on a mission that's never been attempted, using technology that's never been fully tested, heading to a destination about which you know almost nothing. It's an act of faith as much as an act of reason. Faith in the mission, in the technology, in your crew, in yourself. Faith that the journey is worth it, that the destination justifies the sacrifice, that future generations will look back and say it mattered. And maybe that faith is misplaced. Maybe the ship fails, the crew perishes, the mission ends in tragedy. That's a real possibility. We can't eliminate the risk. We can only decide whether we're willing to accept it. This brings us to the final question. Should we attempt the journey to Andromeda? After everything we've discussed, the physics, the engineering, the human factors, The risks, the rewards, the philosophical implications. What's the answer? I don't know. I genuinely don't know. The journey is simultaneously impossible and theoretically achievable, terrifying and inspiring, a waste of resources and humanity's greatest achievement. It depends on your perspective, your values, your vision for humanity's future. What I do know is that the question matters. Thinking about the journey to Andromeda forces us to confront fundamental questions about who we are and what we value. It challenges us to imagine the future, to consider what's possible, to dream beyond the constraints of the present. And even if we never build the ship, even if the journey remains forever theoretical, that act of imagining has value. It expands our sense of what's possible. It reminds us that the universe is vast and full of possibilities. It inspires us to push beyond our current limits, even if we never reach Andromeda specifically. The technologies we develop trying to solve the Andromeda problem might enable other achievements. The questions we ask might lead to insights that transform our understanding of physics, biology, engineering. The dream itself, the vision of reaching another galaxy, might motivate generations of scientists and engineers to pursue careers in space exploration. So maybe the journey to Andromeda is valuable, even if it never happens. Maybe the attempt is what matters, not the achievement. Or maybe we will build the ship. Maybe some future generation will look at the challenges we've outlined tonight and say, we can do this. Maybe they'll develop new physics that makes the journey easier, or new technologies that solve the problems we can't currently solve. Maybe they'll recruit a crew, build the ship, and launch. And maybe, thousands or millions of years from now, humans will walk on worlds in Andromeda. They'll look up at the night sky, see the Milky Way as a distant smudge, and remember that their ancestors came from there. They'll tell stories about the journey, about the brave crew who crossed the intergalactic void. They'll build monuments to commemorate the achievement. And they'll look out at the rest of the universe and ask, where next? Because that's what humans do. We explore. We push boundaries. We reach for destinations that seem impossible. And sometimes, against all odds, we get there. The journey to Andromeda is the ultimate expression of that human drive. It's the farthest we can imagine going with anything resembling current physics. It's the edge of the possible. And standing at that edge, looking out at the impossible distance, we have to decide. Do we step forward into the unknown? Or do we stay where we are, in the safety of the known? There's no right answer. Both choices have merit. Both have consequences. What matters is that we choose consciously, with full awareness of what we're committing to or what we're giving up. And we remember that whatever we choose, the universe will still be there. Andromeda will still shine in the night sky. The stars will still beckon. And future generations will face the same choice we face now: to reach for the impossible or to accept our limits, to explore or to stay home, to risk everything for a dream or to preserve what we have. The journey to Andromeda asks us who we are, and the answer we give defines us as a species. Let me leave you with one final thought. Right now, tonight, Andromeda is visible in the sky. You can see it with your naked eyes if you're away from city lights. A faint smudge in the constellation Andromeda. It's been there all your life. It's been there for all of human history. Ancient astronomers saw it and wondered what it was. Medieval scholars catalogued it as a nebula. Edwin Hubble proved it was a galaxy in the 1920s. And now we know what it truly is. A trillion stars, 220,000 light-years across, 2.5 million light-years away. An entire galaxy, as vast and complex as our own. And it's been there all along, waiting. When you look at it tonight, remember everything we've discussed. The physics that makes the journey so difficult. The engineering challenges that push the boundaries of what's possible. The human cost of leaving everything behind forever. The uncertainty of what you'd find when you arrived. The terrifying isolation of being 2.5 million light-years from home. The philosophical questions about whether the journey is worth it, whether we should even attempt it. All of that is contained in that faint smudge of light. That's not just a galaxy. It's a destination. A challenge. A question mark. An invitation and a warning. It says, I'm here, I'm vast, I'm beautiful. Can you reach me? And we don't know the answer yet. Maybe we never will. Maybe Andromeda will remain forever out of reach, a distant dream that inspires us but never becomes reality. Maybe our descendants will find other frontiers closer to home, other challenges that captivate their imagination and consume their resources. Maybe the journey to Andromeda will be seen by future historians as a fantasy of the early space age, a vision that was never realistic, never achievable. Or maybe not. Maybe right now, somewhere in a laboratory or a university or a space agency, someone is working on the problem, developing new propulsion concepts, new materials, new approaches to life support. Maybe in 100 years, or 1,000, or 10,000, the pieces will come together. The technology will exist. The political will align. The crew will be recruited. And the ship will launch. And somewhere, decades into that journey, the crew will look out the window and see Andromeda no longer as a faint smudge, but as a growing disk of light filling the sky. They'll see individual stars resolving, spiral arms becoming distinct, the bright core glowing. They'll watch as the galaxy they've been traveling toward for decades finally becomes their destination, their new home. And in that moment, everything will have been worth it. All the sacrifice, all the risk, all the years of preparation and travel. Because they'll have done something no human has ever done. They'll have crossed the intergalactic void. They'll have reached Andromeda. Or maybe it won't work out that way. Maybe something will go wrong. The ship will fail, the crew will perish, the mission will end in tragedy. And back on Earth, millions of years later, historians will note the attempt. They'll record that humanity tried to reach Andromeda and failed. They'll analyze what went wrong, learn from the mistakes, perhaps try again. Or perhaps give up entirely, concluding that some destinations are simply too far. We won't know which of these futures comes to pass. We're too early in the story. We're at the point where the journey is still theoretical, still in the realm of imagination and calculation rather than metal and fuel and crew. We're asking the questions, not yet answering them. And that's okay. Every great achievement begins with questions. With someone looking at the impossible and asking, what if? What if we could fly? What if we could reach the moon? What if we could cure disease, split the atom, decode the genome? What if we could reach another galaxy? All of these began as impossible dreams, and some of them remained impossible. But some didn't. Some became reality because people refuse to accept the limitations, refuse to stop asking questions, refuse to give up on the dream. The journey to Andromeda might be one of those dreams. Or it might not. Time will tell. But in the meantime, we can do what humans have always done. We can imagine. We can calculate. We can plan. We can develop the technologies that might someday make it possible. We can train the people who might someday make the journey. We can ask the hard questions about whether it's worth it, whether we should do it, what it means for our species. And we can look up at the night sky, see that faint smudge of light called Andromeda, and feel the pull. The same pull that drew our ancestors out of Africa. The same pull that sent Polynesian voyagers across the Pacific. The same pull that drove explorers to the poles, astronauts to the moon, rovers to Mars. The pull toward the unknown, toward the horizon, toward what's next. That pull is part of being human. It's in our DNA, metaphorically, if not literally. We're a species of explorers. We're uncomfortable with boundaries. We want to know what's on the other side. Andromeda represents the ultimate other side. The farthest destination we can see, the edge of what might be reachable. And whether we ever get there or not, the journey has already begun. It began when the first human looked up at that smudge of light and wondered what it was. It continued when astronomers measured its distance and realized how far away it is. It continues now as we calculate trajectories, develop technologies, imagine what it would take. And it will continue into the future, as long as there are humans who look up at the night sky and refuse to accept that some things are impossible. Because here's the thing about impossible. It's a word we use for things we can't do yet. Things we don't know how to do with current technology and current understanding. But impossible doesn't mean impossible forever. It means impossible now. And now is temporary. Now changes. Technologies improve. Understanding deepens. Impossible becomes difficult. Difficult becomes achievable. Achievable becomes routine. This has happened throughout history. Flying was impossible until it wasn't. Reaching the moon was impossible until it wasn't. Curing smallpox was impossible until it wasn't. Communicating instantly across the globe was impossible until it wasn't. All of these were impossible at some point. And then humans made them possible. Maybe the journey to Andromeda is the same. Maybe it's impossible now, but won't be forever. Maybe our great-great-great-grandchildren will look back at our calculations, our concerns, our doubts, and smile, because they'll know something we don't. They'll know that we figured it out, that we solved the problems, that we built the ships and sent the crews and established colonies in Andromeda. Or maybe they'll look back and understand why we didn't. Why we chose to focus on other priorities, other frontiers, other achievements. Why we decided that Andromeda was a step too far. Either way, they'll know more than we do. They'll have the benefit of history, of seeing how things actually turned out, rather than speculating about possibilities. We're stuck in the present, looking forward into uncertainty. They'll be in the future, looking back at fact. But that doesn't diminish the value of what we're doing now. Asking these questions, imagining these possibilities, calculating these trajectories. Because this is how the future is built. Not through certainty, but through vision. Not through knowing what will work, but through trying to figure it out. Not through accepting limits, but through testing them. The journey to Andromeda, whether it happens or not, pushes us to be better, to develop better technology, to ask harder questions, to imagine bigger possibilities. And that's valuable, regardless of the outcome. So, tonight, when you look up at Andromeda, don't just see a galaxy. See a challenge. See a question. See humanity's ambition and limitations reflected back at us. See the impossible distance and the incredible possibility. See the terror and the wonder. See everything we've talked about tonight compressed into a faint patch of light. And ask yourself, what would I do? Would I go? Would I leave everything behind for a chance to reach another galaxy? Would I risk my life, my future, my connection to everything I know for the opportunity to be part of something historic? Or would I stay? Would I choose stability over adventure, safety over risk, the known over the unknown? There's no wrong answer. Both choices have their own validity. But thinking about the question, really considering it, tells you something about yourself, about what you value, about what kind of person you are. And collectively, as a species, these individual choices add up. They shape our culture, our priorities, our future. If enough people say yes, if enough people want to reach for Andromeda, then maybe we will. If most people say no, if the risks and costs seem too high, then maybe we won't. Either way, the choice is ours. The universe isn't making us go to Andromeda. It's not pulling us there. Andromeda will continue to exist, whether we reach it or not. The decision is entirely human. It's up to us. And that's both empowering and terrifying. We have the power to attempt the impossible. We have the power to reach for another galaxy. But we also have the power to say no, to choose differently, to focus elsewhere. The responsibility is ours. Thank you for spending this time with me tonight, exploring what it would really mean to journey to Andromeda. We've covered a lot of ground. The physics of relativistic travel, the engineering challenges of building a ship that could survive the journey, the human factors of isolation, confinement, and permanent separation from Earth, the uncertainty of what we'd find at our destination, the philosophical questions about whether the journey is worth attempting. All of it pointing to one conclusion: the journey to Andromeda would be the most difficult, most dangerous, most ambitious undertaking humanity has ever attempted. It would push every limit we have: physical, technological, psychological, philosophical. It would force us to solve problems we've never faced, to develop technologies we've never imagined, to make sacrifices we've never contemplated. And it might fail. The crew might not make it. The technology might not work. The destination might not be what we hoped. But if it succeeded, if humans walked on worlds in Andromeda, it would be the greatest achievement in the history of our species. It would prove that there are no boundaries we can't cross, no distances too far, no challenges too difficult. It would make us a multi-galactic species. Citizens not just of Earth, not just of the Milky Way, but of the universe itself. And that vision, that possibility, is worth considering. Even if we never attempt the journey, even if it remains forever a dream, because dreams shape reality. What we imagine, we eventually build. What we envision, we work toward. What we believe is possible becomes possible through our belief and our effort. The journey to Andromeda might be impossible now, but maybe, just maybe, it won't be impossible forever. And when future generations look back at us, at this moment in history, when we first seriously contemplated reaching another galaxy, maybe they'll see this as the beginning. The first step in a journey that would take millennia to complete, but had to start somewhere. And it started with us, looking up at the night sky, seeing a faint smudge of light, and asking, "What if?" Good night, and keep looking up. The stars are waiting. Every member of the crew would need to understand, before launch, that they're leaving everything behind forever. Their families, their friends, their entire civilization will be gone by the time they arrive. There's no going home. Earth, as they know it, will cease to exist during their journey. This isn't a trip to Mars where you might see your family again in a few years. This is a permanent, irrevocable separation from everything you've ever known. The crew would need to be extraordinarily resilient, mentally and emotionally. They'd need to form a stable, self-sustaining community aboard the ship. Conflicts would need to be resolved without outside intervention. Medical emergencies would need to be handled with whatever resources are available on board. If someone develops a serious illness or injury, there are no hospitals, no specialists, no advanced treatments beyond what you brought with you. The ship would need a closed-loop life support system, recycling air, water, and waste with near-perfect efficiency. Any loss of resources over time would be catastrophic. There's no way to restock. If your water recycling system loses 1% of water per year to inefficiency, you'll run out long before you arrive. Food is another challenge. You can't carry 30 years' worth of food for the entire crew. The mass would be prohibitive. You'd need to grow food aboard the ship. Hydroponic farms, algae tanks, perhaps even cultured meat. But farming in space, in a closed environment, for decades, is untested. Crops can fail. Pests can infest your growing systems. Disease can wipe out your food supply. You'd need redundancy, backups, multiple independent growing systems to ensure survival. Then there's the question of reproduction. If the journey takes longer than expected, or if you're using a generation ship approach, the crew will age and eventually die. You'd need to maintain a stable population. Children would be born in space, raised in the confines of the ship, educated to take over roles as older crew members retire or pass away. These children would face an existential challenge. They didn't choose this journey. They were born into it. Their entire universe is the ship. Earth is an abstract concept, a place their parents or grandparents came from, but not real to them in any meaningful way. Andromeda is their destination, but it's so far in the future that it might as well be mythology. They exist in a state of permanent transition, neither here nor there. Psychologists call this intergenerational trauma, the burden of a mission they didn't choose, for a purpose that may lose meaning over time. Maintaining morale, maintaining purpose, across generations would require careful cultural engineering. Stories, traditions, rituals that connect each generation to the original mission. Education systems that preserve knowledge and skills. Governance structures that remain stable without external oversight. Let's assume you've solved all of this. You've built the ship. accelerated to near light speed, protected the crew from radiation and dust, maintained life support for the duration of the journey. You've arrived at Andromeda. Now what? The first thing you'd see, as you approach, is that Andromeda is not a single destination. It's a galaxy containing 1 trillion stars spread across 220,000 light-years. Where exactly are you going? Do you aim for a specific star system? If so, how do you choose? You're looking at Andromeda from 2.5 million light-years away, seeing it as it was 2.5 million years ago. By the time you arrive, the galaxy will have changed. Stars will have been born and died. Planetary systems will have evolved. Any civilizations that existed when you left might be gone, or so advanced they're unrecognizable. Choosing a target is like throwing a dart at a board in the dark. You pick a region of space where you think something interesting might be, and hope it's still there when you arrive. And then there's the deceleration problem. You've been accelerating for years, reaching near light speed. Now you need to slow down, or you'll zip through the galaxy and out the other side, having come all this way for nothing. Deceleration requires as much energy as acceleration. If you used a laser sail to accelerate, you can't use it to decelerate unless there's a laser array waiting for you at Andromeda. There isn't. You'd need to carry fuel for deceleration, which brings back the fuel mass problem. Or you'd need some other method. A magnetic sail could interact with Andromeda's magnetic field, using it as a brake. But magnetic fields in interstellar space are weak. Deceleration would take a long time, and you'd need to carefully manage your approach to avoid overshooting. Once you've decelerated, you're in the Andromeda galaxy. Congratulations. You've completed a journey that no human has ever attempted. You're 2.5 million light-years from Earth, in a galaxy that contains 1 trillion stars. What now? Communication with Earth is impossible. Any message you send will take 2.5 million years to arrive. The reply, if there is one, will take another 2.5 million years to return. You're on your own. You'd need to establish a colony, find a habitable world, or build habitats in space. Begin the process of exploring this new galaxy. You're effectively starting human civilization over from scratch, but in a completely alien environment. No infrastructure, no support, no connection to the rest of humanity. And here's a thought that should chill you to the bone. What if, during your 2.5 million year journey, humanity on Earth developed faster than light travel? What if, 1 million years into your journey, humans figured out how to bypass the light speed limit, built warp drives, and colonized Andromeda themselves? You arrive, exhausted, your crew having sacrificed everything, only to find that Earth beat you there centuries ago. Your entire mission was pointless. Or worse, what if you arrived to find Andromeda already inhabited? Not by humans, but by something else. An alien civilization that evolved there, or migrated there from elsewhere. You've traveled 2.5 million light-years to be the first humans in Andromeda, only to discover you're trespassing in someone else's galaxy. How would they react to your arrival? Would they welcome you? Would they see you as invaders? Would they even notice you at all? The sheer scale of Andromeda means your ship, even if it's miles long, is microscopic in galactic terms. You could wander the galaxy for centuries without encountering anyone. This is the existential terror of the journey. Not just the physical challenges, but the uncertainty. You're committing to a mission that will take millions of years from Earth's perspective, with no guarantee of success, no way to turn back, no contact with home, no knowledge of what you'll find when you arrive. You're launching into the unknown, with only faith that the destination is worth the sacrifice. Let's talk about one more challenge: cosmic expansion. The universe is expanding. Space itself is stretching, causing distant objects to recede from each other. Andromeda is currently approaching the Milky Way due to mutual gravitational attraction, so expansion isn't pushing it away from us right now. But for truly distant galaxies, expansion matters. Galaxies far enough away are receding faster than light, not because they're moving through space faster than light, but because the space between us and them is expanding. For Andromeda, this isn't an issue during your journey, but it's a reminder that the universe isn't static. The structure of space and time is dynamic, changing, evolving. By the time you arrive in Andromeda, the universe will have aged by 2.5 million years. Distant galaxies will have receded further. The cosmic microwave background will have cooled slightly. New stars will have formed, old stars will have died. The universe is not a frozen backdrop. It's a living, changing system. Let's step back and ask a fundamental question. Why would anyone attempt this journey? What possible motivation could justify the cost, the risk, the sacrifice? Scientific exploration is one answer. Andromeda is the nearest large galaxy, and studying it up close would revolutionize our understanding of galactic evolution, star formation, the distribution of dark matter, and countless other questions. But sending a probe, not a crewed ship, would accomplish most of the science at a fraction of the cost and risk. Maybe the motivation is survival. If something threatens Earth, a catastrophic asteroid impact, a nearby supernova, runaway climate change, nuclear war, you might send a ship to Andromeda to preserve humanity. But Andromeda is 2.5 million light-years away. If Earth is doomed, you'd colonize the Milky Way first. There are 400 billion stars here, many of them closer and easier to reach. Maybe the motivation is ideological. The belief that humanity must expand, must explore, must reach beyond our cosmic neighborhood to fulfill our destiny. But destiny is a dangerous motivation. It can justify enormous suffering in pursuit of an abstract goal. Or maybe the motivation is simply because it's there. Because Andromeda exists, and we can see it, and the human spirit demands that we reach it. Because exploration is part of what makes us human, and the greatest explorers in history were those who ventured into the unknown, despite the risks. Whatever the motivation, a journey to Andromeda would represent the ultimate test of human capability. It would require technology we haven't invented yet, physics we don't fully understand, social structures we've never tested, and a level of commitment that spans not just lifetimes, but millennia. It would be the most ambitious project humanity has ever undertaken. It would make the moon landing look like a test flight. It would make the International Space Station look like a child's toy. It would be an endeavor that defines a species that pushes us to the absolute limits of what's physically possible. And even if we succeeded, even if we built the ship and launched it, and the crew survived and they arrived at Andromeda, there's no guarantee it would be worth it. The journey itself might be the point. The challenge, the striving, the refusal to accept limits. Or maybe we'll never attempt it. Maybe we'll look at the calculations, the energy requirements, the timescales, the isolation, and decide it's not worth the cost. Maybe we'll focus on the Milky Way, exploring and colonizing within our own galaxy, which is vast enough to keep us busy for millions of years. Or maybe we'll find another way. Maybe future physics will reveal shortcuts through space, wormholes or warp drives, or dimensional bypasses that make the journey trivial. Maybe we'll upload our consciousness into machines that can survive the journey without life support. Maybe we'll send self-replicating probes that arrive at Andromeda and build the infrastructure we need, so that when humans eventually follow, they're arriving at an established colony rather than an empty void. Or maybe we'll never leave the solar system at all. Maybe virtual reality will become so advanced that we can experience Andromeda without physically going there, exploring simulated galaxies that are indistinguishable from the real thing. We don't know. The future is uncertain. But when we look at Andromeda in the night sky, that faint smudge of light, 2.5 million light-years away, we're looking at a destination that represents both the ultimate achievement and the ultimate impossibility. It's close enough that we can see it, study it, dream about reaching it, but far enough that actually getting there would require us to transcend nearly every limitation we currently face as a species. The journey to Andromeda is terrifying, not because of any specific hazard, though there are plenty, but because it forces us to confront the sheer scale of the universe and our own smallness within it. It reminds us that space is vast, time is long, and the distances between galaxies are so great that they might as well be infinite. It shows us that even our grandest ambitions might be constrained by the fundamental laws of physics, that there might be places we can see but never touch, destinations we can dream about but never reach. And yet, there's something beautiful in that impossibility, because it means the universe still holds mysteries beyond our grasp. It means there are still frontiers that challenge us, goals that seem unreachable but inspire us to try anyway. The journey to Andromeda, even if we never attempt it, serves as a North Star for human ambition. It's the ultimate what if. What if we pushed ourselves to the absolute limit? What if we solved every problem, overcame every obstacle, refused to accept any limitation? How far could we go? The answer, at least for now, is Andromeda. 2.5 million light-years away, waiting. A galaxy full of stars, perhaps full of life, perhaps empty and silent. We don't know. And maybe that's the most terrifying thing of all. The not knowing. The uncertainty. The vast gulf of space and time that separates us from the answers. When you look up at Andromeda tonight, remember what you've learned. That faint patch of light represents a journey that would take millions of years, require technology beyond our current understanding, demand sacrifices we can barely imagine. It represents the edge of what might be possible, the boundary between the achievable and the forever out of reach. And maybe, just maybe, that boundary isn't as fixed as we think. Maybe future generations will look back at our calculations, our assumptions, our limitations, and laugh. Maybe they'll board ships that cross intergalactic distances in days or hours, using physics we haven't discovered yet. Maybe they'll arrive at Andromeda and build civilizations there, turning that distant galaxy into a second home for humanity. Or maybe they won't. Maybe Andromeda will remain forever beyond our reach, a reminder of the universe's vastness and our own limitations. Either way, the journey to Andromeda, real or imagined, tells us something important about who we are as a species. We're creatures who look up at the night sky and don't just see beauty, we see destinations. We see challenges to overcome, mysteries to solve, places to explore. We're not content to stay where we are. We're driven to reach further, to push harder, to see what's on the other side of the horizon, even when that horizon is 2.5 million light-years away. That drive is both our greatest strength and our greatest weakness. It's led to incredible achievements, but it's also led to suffering, to failed expeditions, to lives sacrificed in pursuit of impossible goals. The journey to Andromeda would be the ultimate expression of that drive. It would be humanity saying, "We see the impossible, and we're going to attempt it anyway." Not because it's easy, not because it's safe, but because it's there. Because the universe challenges us to reach it, and we can't help but respond. Thank you for taking this journey with me tonight. We've explored what it would take to cross the gulf between galaxies, the physics, the engineering, the human cost. We've looked at the terrifying challenges and the uncertain rewards. And we've confronted the possibility that some destinations, no matter how much we want to reach them, might remain forever beyond our grasp. But maybe that's okay. Maybe the value isn't in arriving, but in daring to try. Maybe the journey itself, the dreaming, the planning, the pushing of boundaries, is what defines us. Maybe Andromeda's greatest gift isn't as a destination, but as an inspiration. A reminder that the universe is vast and full of wonders, and that we're a species that refuses to accept limits. Next time you look up at the night sky and see that faint smudge of light in the constellation Andromeda, think about what it represents. Not just a galaxy, but a challenge. Not just a destination, but a dream. And maybe, just maybe, the impossible isn't as impossible as it seems. Good night, and keep looking up.